about determining the concentration of electrons and holes in a semiconductor, okay, given the doping that you put in the material. So suppose you have, in general, a semiconductor that's doped with both donor and acceptor doping. Then the overall doping in the semiconductor, the type of the semiconductor, depends on essentially the net doping, right? Which one is the larger component, whether it's the donor doping or the acceptor doping. So if you have all this information, how do we then determine the N0 and P0? So we mentioned that there's actually two sets of equations that you can use to relate N0 and P0, and this essentially allows us to solve the equations simultaneously so that we can effectively work out the N0 and P0 values. The first equation, of course, is your mass action law, where you have the product of N0 and P0 being always equal to Ni squared. And the other expression is our charge neutrality equation, okay, which is a relationship relating your hole concentration, electron concentrations, and the dopings in your semiconductor. Okay, so in fact, we've gone through this derivation for various cases, right? Whether it's just a single doping or it's multiple dopings of N and P type. Okay, in general, right? In general, if you have both dopings, then we find that the majority carrier concentration can be determined from this solution here of a quadratic equation, which involves the net doping plus square root net doping squared plus 4n squared over 2. And of course, if your net doping is much greater than Ni, then you find that your majority carrier concentration is just simply the net doping value. Okay, because the Ni here becomes negligible, and your net doping is essentially just 2 times in the numerator divided by 2 in the denominator. You get back just the net doping. Okay, so in the case where the doping is large, then we can just approximate the major carrier concentration to just the net doping. Of course, once you have the carrier concentration for the majority carrier, then the minority carrier can easily be determined using the mass action law, where you divide the Ni squared with the majority carrier concentration. Okay, so this process here basically does not require a knowledge of the position of the Fermi level in the semiconductor. All right, this is independent of the knowledge of Fermi level, where we just need to know the dopings and the intrinsic carrier concentration in a semiconductor. And in fact, this process here to determine the carrier concentration, coupled together with the equations that relates concentration to Fermi levels, right, allows you to then determine the position of Fermi level in your semiconductor. And if you recall, there's actually these two sets of expression that you can use. They are essentially the same, right? One relates to the effective density of state, NCMV, and the other set of equation, it's kind of derived from this set here, but we express it in terms of Ni. Okay, so essentially it depends on what quantity you have on hand. Okay, you basically choose the suitable set that allows you to use those values that you know. Okay, if you know Ni, then of course you will use this first set of equation here. If you know the effective density of states of the semiconductor, then you can use this second set here. Okay, so either one you use, the solution for the Fermi level, it's essentially the same. Okay. Now next, we then move on and talk about carrier transport, which essentially relates to the movement of carriers in a semiconductor. This is essentially important because when you look at a semiconductor device, the operating one, right, essentially will have some sort of current that's flowing in the semiconductor. And we mentioned that there are essentially 2 types of carrier transport. One is called the drift, which is due to a presence of electric field. So this is driven by electric field. Okay, so causing the carrier to move and thereby generating a current. Okay, so that's your drift. Okay, the resulting current is a drift current. The other process is a diffusion process, where if you have some difference in concentration of carriers in different parts of the semiconductor, you will get a diffusion process going on where region where there's higher concentration of the carrier would diffuse to regions where there is lower concentration of carriers. Okay, so this diffusion process would of course lead to a current flow, right? Because the charge is moving, so current results. And this is known as diffusion current. Now, of course, the movement of carriers under the carrier transport mechanism that we mentioned is under some, essentially some force that's present, right, that results in the carriers moving. Under thermal equilibrium condition, in fact, you will also find carriers moving as well. Okay, under this thermal motion with thermal energy that's available, carriers basically have the thermal velocity where they sort of randomly move about. And the importance difference between this and the carrier transport process is that, first of all, it is a random process. Okay, there isn't a directed motion, implying that you do not get current out of this. Okay, although the carrier is sort of moving around, the net position of the carrier does not change. Okay, so if the position doesn't change, you don't get current. Okay, so thermal motion basically causes the carrier to kind of rattle around in the semiconductor, okay, without a net movement in the position. Okay, so we also talk about a parameter, okay, that basically describe how fast the carrier can move in a semiconductor under the presence of electric field. We find that the retrieve velocity of your carrier is basically related to, of course, the electric field that is applied, right? The electric field is like a force that will push the carrier, and how fast the carrier essentially moves depends on another parameter called the mobility. Okay, so the mobility is basically like a parameter of the carrier in a particular semiconductor that describes how fast it can move per unit electric field, okay, that is present. So this is basically a material dependent parameter. In different materials, the electrons at home will move differently with different mobility value. Okay, and from the discussion, we also kind of derived that the mobility is given by this expression here, Q tau C over M star. So tau C is the average time between collision, and the M star, of course, is the effective mass of your carrier in the semiconductor. Okay, and what essentially affects the mobility, how fast the carrier can move, per unit electric field that is present, is essentially limited by scattering mechanisms. Okay, so in a semiconductor, we mentioned two scattering mechanisms. The first is lattice scattering, or sometimes we call this phonon scattering. This results from the vibration of the atoms in the crystal when the temperature is non-zero. Okay, so when you're at some temperature, the atoms in the lattice actually will vibrate, and the higher the temperature, the sort of larger amplitude that will vibrate, and the chance of a moving carrier interacting with the vibrating atoms will increase, right? If it's going to vibrate with a larger amplitude, then the chance of a carrier encountering the atom, right, will be higher, which in turn then could knock it off from its initial directed motion. Okay, so you get kick around, right? So this is called a scattering process. It's the carrier gets scattered in a different direction. So this increased scattering would, of course, reduce the average time between collision, right? If it's going to be scattered more frequently, the time that it can move freely without scattering is going to be shortened, okay? And this in turn will affect how fast it can move, right? The time that it has to accelerate to higher velocity is lesser. So, which means that the mobility of the carrier actually will reduce. So in terms of dependence on lattice scattering, or rather effect of lattice scattering on mobility, right? When the temperature changes, it essentially would reduce the mobility of your carrier, okay? Based on this mechanism. If the lattice scattering is the main mechanism that limits the movement of carrier. Now, the other scattering mechanism we can find in a semiconductor is what we call the ionized impurity scattering. As the name implies, it arises from the ionized impurity atoms in a semiconductor. So obviously, this will tell you that this will be present when the semiconductor is doped. Okay, there is impurity atoms in the crystal, and this ionized impurity is essentially carrying a charge. So when the carrier moves near to it, you exert a force on the charge because of the charge, right? And this will cause the carrier to deviate its movement, its path, right? And this can affect the mobility as well. So of course, there's two things that would affect your mobility. The first is the concentration of the ionized impurity atoms in the crystal. Obviously, if the doping is high, this number of impurity atoms per unit volume will be higher, and which means that the chance of a carrier encountering these ionized impurity atoms will also be higher. Okay, which means that the average time between collision would decrease. So it's more likely to encounter ionized impurity atoms, and it's more likely for the carrier to be scattered, okay, implying that the mobility would decrease if there's a lot of them, right? In terms of temperature dependence, we find that in the case of ionized impurity scattering, when the temperature increases, the thermal velocity of the carrier actually goes up. So if it has a higher thermal velocity, when it gets near to one such ionized impurity atom, it actually does not spend so much time near it. So if we actually spend less time near it, then its path of movement, right, actually gets less affected. Okay, so in other words, it gets scattered less. Okay, and the average time between collision actually will go higher. Okay, you can actually go longer distance without being scattered so much. Okay, so the tau c actually increases under this mechanism, and in fact, you find that the mobility actually goes up when temperature increases. Okay, that's provided the ionized impurity scattering is the main scattering mechanism, right? Okay, so these two scattering mechanisms actually has different effect on mobility when temperature changes. And in fact, by looking at how the mobility varies, right, when the temperature changes, you can tell which is the dominant scattering mechanism in the semiconductor. Okay, so then we went on and derived the equations for the drift current density in a semiconductor. So under the presence of electric field, if you have some concentration of electrons and holes, then what is the resulting current that's flowing in the semiconductor? Okay, so we did a derivation for this, and we find that the drift current density, whether for electrons and holes, is given by the product of the charge, Q, with the concentration of the carriers, okay, depending on whether you're looking at electrons or holes, and the corresponding mobility and the strength of your electric field. Okay, and of course, in a semiconductor, you typically have both carriers present in the semiconductor. So the total current density that you would see is the sum of these two terms. And in fact, you take out electric field as a common factor, right? The rest in a bracket is commonly known as the conductivity of the semiconductor. Okay, and this conductivity is related to resistivity by a reciprocal term, right? Which is essentially the same for the conductivity and resistivity that you use for regular conductors or resistors, right? Okay, so this really depends on two things now: your concentration of the carriers and the mobility of the carriers. In fact, in our last discussion, we also mentioned that this drift current density equation, right, for your semiconductor is none other than your Ohm's law. Okay, so this is really just your Ohm's law. Okay, so which is not surprising because Ohm's law basically allows you to describe how much current you get with a voltage that's applied, right? Which it's basically describing how carrier move under the influence of electric field, right? You have a voltage electric field will be set up. So similarly, in the case of drift current, this pertains to the movement of carrier under the presence of electric field. So it should not be surprising to you that this is really just Ohm's law, okay? Now for today's discussion, we're going to cover the other transport mechanism, which is the diffusion current. So as I mentioned, the key point about this diffusion process is that it's a flow of carriers from high to low concentration, right? And this is in fact, arising from the fact that the carriers are sort of randomly moving, right, under thermal effects. Okay, and this thermal effect basically will help to redistribute your carriers until you achieve equal concentration everywhere. Okay, so that's what the random thermal motion will do, right, if you have a concentration imbalance. So to basically analyze this and try and come up with an equation to describe the diffusion current, right, like what we did for the drift current, we would similarly consider a one-dimensional case, right, in a semiconductor. Okay, so of course in this discussion here, we are also assuming that the temperature in the semiconductor is uniform, right? So that the thermal energy that carriers have everywhere is the same. Okay, so how do we derive this diffusion current density in your semiconductor? So here we have, let's say the electron density in a semiconductor. So plotted on in this graph, okay, vertical axis is your electron density, horizontal axis is position in the semiconductor. Okay, so let's say we look at some position in the semiconductor at some point x equals to 0, right? This point here. So the corresponding concentration there is a function n at x equals to 0, n0, right? And how do we basically determine the diffusion current that results from this process? So you see that the curve here basically tells us that the concentration of electrons is changing, right? It's different at different points, where it's more on the right-hand side and it's less on the left-hand side, okay? So obviously you expect this to result in a diffusion occurring, and the diffusion will occur from right to left, okay? Because the right side has more electron concentration, so you're going to expect a net flow of electrons, okay, from right to left. So how do we derive the resulting diffusion current? Okay, so to carry out this derivation, what we can do is we consider some position L to the left and right of this reference point x equals 0 in the semiconductor. Okay, so this L here is a term called the mean free path, okay, which is essentially the average distance that an electron can travel between collisions. That means before they get scattered, okay, the sort of free path that it can move before it gets scattered. So this would essentially guarantee that, if let's say for example, this carrier at x equals to minus L, right? If it moves to the right, okay, within the L distance, you guarantee that it will pass through x equals 0. Okay, so you pass through x equals 0, then at x equals 0, you register a current. Okay, as long as the carrier crosses the cross-sectional area, you get a current. Okay, so that's why you consider a mean free path L. So what is how do you determine the mean free path in this case? So as the definition goes, right, L is a mean free path. So it's basically the average distance that the electron travel between collision. Previously, we talked about tau c, the average time between collision, right? That's kind of like the time where the carrier can move freely before it collides on average. So if we multiply this time with the thermal velocity of the carrier, okay, this would give you the mean free path. Okay, velocity times times give you the distance that the carrier can move freely before it collides. Okay, so the L is simply related to the product of the thermal velocity and the average time between collision. All right. Now, so another thing that we will do as well is to make an approximation, okay, to relate to the concentration at n0. So, of course, at the point x equals minus L, the concentration at that point there is n of x equals minus L, and on the right-hand side at position x equals L, this concentration here is n of L. Okay. So, of course, if you look at this distribution of the electron density, the curve, it is not a linear curve, right? And so one thing that we could try and do is to try and do approximation of this concentrations here in terms of n naught, okay, the concentration in the middle that we're considering. Okay, this is necessary because later on we see that we're going to make use of this approximation to simplify the calculation. Okay, so how do we relate, for example, n of minus L to n of 0? Okay, so what we can do is that if you look at the figure, right? Okay, how do we approximate the N or L value to N0? Okay, so we can do that by doing a very simple approximation, which I think most of you have learned before. Okay, if I have information about the gradient at x equals 0, that means I know what is dn dx at x equals 0, right? Okay, then what I can do is, if I have to try and draw a straight line to this point, okay, extending to both sides, then you can see that if the L is relatively small, okay, if L, that means this horizontal distance here is relatively small, then this gradient, okay, which we have drawn here, right, it will basically give us a relatively good approximation, okay, estimate to the value on this curve, right, to the left and in fact to the right as well. Okay, this approximation will be relatively close to the true values. So if we look at n of minus L, how do we get the vertical value? Okay, so the idea is that we want to find out what is this value here, right? So what approximation can we do to estimate this value? So if you consider, okay, the value at x equals 0, which is this value here, so I need to subtract n of 0 by this amount here, right? Okay, so if you use the gradient of the straight line that we put, or the tangent that you put at x equals 0, okay, we put a tangent at x equals 0, then this gradient here up to the minus L on the left hand side, right? And using the gradient, assuming that this is a straight line, then we can basically estimate this amount here. Okay, so we call this h. Then we can write down h as a product of L with dn dx. Okay, someone has turned on the mic. Can you switch off the mic, please? Thank you. Okay, so we can actually estimate this vertical distance that we have to move down, right, to give an estimate to n of minus L. Okay, so using the gradient at x equals 0. Okay, so we can estimate this h here as, okay, we can estimate the h. Oh, sorry. Okay, the h is the difference between x equals 0 and x equals minus L, right? Okay, so this h here can be estimated from the product of the L, right, this horizontal distance here, with the gradient at x equals 0. Okay, so if we do a n0, oh, sorry, here. Okay, if we do an n0 minus L dn dx, then that gives us a estimate to n of minus L. Okay. So similarly, for n of plus L, if you want to estimate it from the gradient, right, as we did for n of minus L, then you can basically use the same process. Okay, so again, using this tangent that you draw, right, if you want to do an estimate, then we can say that this is given by n of 0 plus this little bit here, which we can kind of estimate from this other h. Okay, so we know this is L. All right, if you know the gradient, of course it may be off a little bit, but if your L is small, then this difference is negligible. Okay, so similarly, your h is still L multiplied by dn dx. Okay, so for the point on the right hand side, we can estimate it as n0 plus L dn dx. Okay, so this is the approximation I can use. Of course, sort of fanciful name for this is what I call Taylor series expansion, right? Okay, Taylor series is basically a series representation of the curve using gradients or derivatives, okay, at a particular point, right? Multiple derivatives. So in the case of Taylor series, we just take the first order derivative, the first term, and then the rest we ignore. Okay, that gives you a rather good approximation, right, to the values on the left and right. that is near to the point they are considering. Okay, that's Taylor series. Okay, but the bottom line is that, you know, this is essentially just using the gradient of tangent at the reference point and sort of estimating using the gradient of the tangent for the values on the left and right hand side. All right. Okay, so how do we then find the resulting current, right, that's flowing in our semiconductor? So, okay, let me get rid of this. Okay, so the idea here, right, in terms of derivation is this. So if you want to find the current that's flowing through x equals to 0, right? So we want to find out what's the current that's flowing through this plane here, okay? Because if you find the amount of charge that's flowing through a cross-sectional area, then you find current. Okay, so in this case, for these 2 points, right? So if we look at carriers on the left and right hand side of this carrier, right, or this reference point x equals 0, the carriers at x equals minus L, okay, these guys here, right, basically are moving randomly under thermal effects. So this means that there's an equal chance for this carrier to move left and to move right, okay? And obviously the carrier that moves right is going to cross your x equals 0 reference point, and this will result in current, okay? And how much will flow left and right? Because it's a thermal process, it's a random thermal process, what you expect is that half of these guys, right, half of n or minus L is going to flow left, and the other half is going to go right. So the one that goes right is going to give you the current, okay? That's from carriers at x equals minus L. And similarly, by the same argument, okay, for carriers at x equals L, half of them will flow left and half will flow right. So the one that flow left is going to go through your x equals 0, right? And this number here is also half n of L. Okay, of course, the other half n of L that goes the other way, it's not going to cross through that area. Okay, so what you can see here is that really the component that would give rise to current, right, at x equals 0 would be this guy. Okay, this guy is that move to the right from the left hand side, and this component that moves to the left from you know, the concentration on the right hand side. Okay, so these two will contribute to the current. So the resulting current that you're going to get, right, due to diffusion is the net effect due to these two components. Okay, so here we can then write down what we call the electron flux, okay, represented by this symbol here. Okay, that's basically describing the average number of electrons that crosses x equals 0 per unit area per unit time. Okay, in the positive x-axis direction. So so if you go back, right, the net effect will be this amount that goes in the positive direction minus this amount that goes in the negative x-axis direction. So it's half of n minus L, right, minus away the half n of L. So half n minus L, this is the carrier concentration, right? But we want to find out how many crosses it per unit area per unit time. So we multiply it with the thermal velocity of the carrier. Okay, that's why you see there is a VTH there. Okay, in terms of unit, you can basically work out that, you know, it will give you the number per unit area per unit time, right? Because if you analyze the units, this concentration here is per centimeter cube, right? Number per cubic centimeter, and the velocity, thermal velocity, is, if you put it in centimeter, length per unit time. Okay, so if this cancel out, then you're left with resulting unit is per centimeter square and per second as the unit. Okay, so that basically gives you the number of electrons that will be flowing per unit area, because it's per length square, right? That's like per unit area and per unit time. Okay, so we multiply the concentration with the velocity, you get essentially the electron flux. All right. So of course, with just n minus L and NL, we can actually put in the approximation that we made earlier in terms of N naught and the derivative of the concentration. Okay, so that you get an expression that is, can tell you something about how the gradient will basically affect the flow of the carriers. So we put in those approximation. For N naught minus L is N naught minus L dn dx. For N naught L, as I mentioned before, is N naught plus L dn dx. This actually allows you to cancel out some of the terms, right? You notice that the N naught actually cancel out. Okay, the L dn dx actually would add on, and we get the electron flux as minus VTH times L. Okay, and then you have the derivative dn dx. Now this VTH times L, okay, we collectively call this dn, which is the electron diffusion coefficient, or the electron diffusivity of your semiconductor carriers. Okay, so this basically describes how fast the carrier can diffuse given a concentration gradient in the semiconductor. Okay, that's the electron diffusion coefficient. This basically is the electron flux. Okay, how many electrons are flowing per unit area per unit time? How do you find the current? If you know how many electrons are actually flowing per unit area per unit time, we just need to multiply the quantity with Q, right? You multiply with Q, then you get Coulomb per unit area per unit time. Okay, so if you do that, you multiply the Q, in this case minus Q because it's electron, right? So the charge is actually negative. Okay, so negative. So again, we analyze the units. We have the charge, which is Coulomb, and the electron flux, as I mentioned earlier, is per unit area per unit time. Okay, so the charge per unit time charge per unit time is essentially your current, right? Okay, this is your current. Okay, Coulomb per second is essentially your ampere. Okay, so in other words, okay, this quantity that we're calculating is ampere per unit area, right? This is area. That means we're actually getting the current per unit area, which is your current density. Okay, so this term here actually gives us the current density. Okay, that's why we write it as Jn diff. Okay, so this is a current density quantity. So in the case of electron current density, you find that it's simply the product of the charge with the diffusion coefficient of electrons and the gradient of the concentration in the semiconductor. Okay, that's what it depends on. So you can actually do a similar analysis for the case of holes as well, and you basically get a similar expression. It's still charge multiplied by the diffusion coefficient of hole in this case, okay, and the concentration gradient of holes in the semiconductor. Notice that the main difference here is the presence of a negative in the case of hole current density. For electron diffusion current density, you find that it's actually positive, and this is again not surprising if you think about it, right? So if you consider a case where both electrons and hole carrier concentration has positive gradient, right? Then you find that in the case of electron concentration, okay, the flow will be from right to left because the right side is higher concentration. In the case of holes, similarly, because it's a positive gradient in terms of particle, right, you flow from right to left. But this net flow of charges from right to left, in the case of electron, will mean that the conventional current is in the opposite direction, okay, which is in the positive x-axis direction. So this is considered positive current. In the case of holes, hole is moving to the left, positive charge moving to the left. That means your current basically follow the direction of positive charge, which is to the left as well. So if the conventional current is to the left, it's in the negative x-axis direction. This is treated as negative current. Okay, So that's why you get this difference in the sign. Although the carriers move in the same direction because they are charged, the resulting conventional current you get is in opposite direction. Okay, so which one is negative? Actually, you can, okay, which one is positive, which one is negative, you can't remember, you can actually just draw this graph and then you can figure it out. But of course, the other thing is that in the formula list, we do give you the formula. So you can also refer to the formula list to see which one is positive and negative. Okay, but in fact, if you don't have that, you can still figure it out if you understand how it comes about. Okay. So, okay, so of course, in a semiconductor, if you consider the electrons as whole separately, right, then you can basically write down the total electron current density as being made out of two components, one due to drift and one due to diffusion. Okay, of course, if the electric field is not there, then the drift component will disappear. Then you just have diffusion if you have a concentration gradient, and vice versa. Okay, so the same goes for holes. And in reality, the total current that is flowing, right, in a semiconductor will be made out of the sum of all these four components, because there are two carriers, and each carrier has two different transport mechanisms. So total, you have four current components to consider. Of course, most times, in terms of analysis, you will find that usually the majority carriers will be the dominant component because the quantity there is the largest, right? So usually it's the majority carrier that will dominate in terms of the current that's flowing in the semiconductor. Okay, but in reality, it's made up of four components. Okay, and which one is negligible? You have to look at the specific scenario that you're analyzing. Okay, those that has smaller component for the current, right, respective current, you can ignore. And through there, you can usually reduce the number of components that you need to deal with to a smaller number instead of all four. Okay. Right. Okay, so in fact, there is another thing which I also need to mention, which is that between the diffusion and the mobility, right, it turns out that there's actually a link between these two. Okay, the diffusion coefficient and the mobility are actually related to each other. Okay, so we can actually derive this. If you start with the electron diffusion coefficient, which we, as you can see from the previous derivation, is defined as the product of the terminal velocity with the mean free path, L. Okay, so we know mean free path is the product of the terminal velocity and the average time between collision, tau Cn, for electrons. If you put this in, then you get the diffusion coefficient of electron as terminal velocity squared multiplied by the average time between collision. Now, if we consider a one-dimensional case, the terminal velocity of your electron will be just half kBt, right? And this is essentially kinetic energy that the electron have. So if you do a half mv squared to half kBt, okay, where in this case we have to use the effective mass of electron because it's in the semiconductor, so we have to use the effective mass. And the velocity in this case will be the terminal velocity of your electron. So this allows you to find out what is the terminal velocity VTH, which you can then put it into the previous expression of the electron diffusion coefficient, and you find that it reduces to kBt over effective mass multiplied by average time between collision. Okay, and in this case, you find that there are actually some terms that you can relate to the electron mobility, right? If you recall, the electron mobility is given by this expression here, which is the ratio of the average time between collision and the effective mass. And from this diffusion coefficient term, right, we see that there is a average time between collision, there's an effective mass in the denominator. Okay, so using these terms here, right, you can see that the tau Cn over the effective mass is just equals to the mobility of electron over the charge. Okay, so if we replace the tau Cn over effective mass with mobility over Q, then it reduces to this simpler form, okay, which says that the diffusion coefficient of electron is given by kBt over q multiplied by the mobility of electron. Okay, so these two are actually related, okay, by this temperature term here, right? So it's actually related to temperature. So similarly, you can do the same derivation for holes, and you will find that you get a similar expression to that of electron. Okay, so these equations here are called the Einstein relation, which relates diffusion coefficient to mobility. So the reason why they are related parameters, right, it's essentially because if you look at these two mechanisms of drift and diffusion, okay, what's the underlying process that limits how fast the carriers can move? And you will see that it's essentially the scattering mechanism. Okay, whether it's drift or diffusion, okay, how fast and how far they move, it's limited by scattering mechanism in the semiconductor. So there's actually this common process, right, that's involved in these two mechanisms that limits how fast they can go. Okay, and that's the basis of your Einstein relation. Okay, they are related by that. Now, if you look at the mobility and diffusion coefficient of different semiconductors, the typical ones like silicon, gallium arsenide, germanium, you can see that mobility of, in this case, of all these three semiconductors, they are higher than that of mobility of holes, right? Electron is higher than that of holes. And in fact, if you know these parameters, one of the parameters, and the knowledge of temperature, you can essentially work out the other parameter. Okay, as long as you know the temperature, you can use the Einstein relation to find out the other parameter. Okay, so this is actually a useful relation that allows you to determine one parameter from another if you know the temperature. Okay, then the next thing that I'm going to just briefly discuss, right, is the characterization of semiconductors. Okay, so this part here would not be examinable. Okay, in other words, the test and exam will not cover this. Okay, but we need to discuss this because in your lab experiment, right, your lab 2, we're going to use some of this characterization technique. So it is obviously important that you understand the principle behind these experiments so that you can do your experiment. Okay, so I'm going to discuss this just very briefly so that when you go to lab 2, you'll be more aware of what's going on in the semiconductor, in characterizing the semiconductors. So there are actually many characterization techniques in the field of semiconductors to basically measure various quantity of the semiconductors, things like mobility, diffusion coefficient, carrier concentration. Okay, requires you to basically do some measurement so that you can infer these semiconductor parameters. Okay, so here we're going to cover a few. Okay, the first one that I'm going to talk about is what we call the Hall effect measurement, which is a very useful experimental technique that allows you to actually determine many parameters in the semiconductor. So this figure here basically shows the typical setup for the Hall effect measurement. And what you see here is essentially a piece of semiconductor, right, with a dimension of L for length, D for the width. No, okay, it's not the width, it's the depth, and W is the width. Okay, so we have this rectangular piece of semiconductor, okay, that is connected to a voltage source in the long direction, right? So you see that in the long direction, we basically connect the semiconductor to a battery source or power source, voltage V applied. And in doing that, of course, we expect a current flow in the semiconductor, okay? And in the vertical directions, okay, we basically make contact to somewhere in the middle of the top and bottom surface, okay, and we connect this to essentially a voltmeter. Okay, connect to a voltmeter and we try to measure the voltage at these two positions. Okay, so if you think about this, right, you have now a current that's flowing through the semiconductor. then the question here is, what is the voltage difference between 0.3 and 0.4, right? The point at the top and the point at the bottom. So the way to think about this is that if you consider the kind of like the resistance from the phase 1, right, from the side labeled as 1, okay, this phase here, to 0.3, for example. Okay, so there's actually a path that goes through a semiconductor. So you can think of this as like a resistive path. Okay, and similarly, for the path from 1 to 4, okay, there's similarly a resistive path, right? Now, if I make contact to the top and bottom at the same distance from the edge, that means this distance from 0.3 to 0.1 and from 0.1 to 0.2, right, it's essentially the same, then it means that the resistance between 1 and 3 and 1 and 4 must be the same. Okay, so if the resistance is the same, then you would expect the voltage dropped from 1 to 3 and 1 to 4 to be the same as well. Okay, so if let's say the voltage drop from 1 to 3 is V, then the voltage drop from 1 to 4 will also be V, right? And in this case, then what is the voltage difference, right, or the potential difference between 0.3 and 0.4? Okay, it will simply be the difference between these two voltage that we mentioned, right? This V minus this V here, and you'll find that the potential difference between 0.3 and 0.4 will be 0. Okay, so if you put a voltmeter here, right? So you put a voltmeter at the end of the 0.3 and 0.4, your voltmeter will measure 0 volt. Okay, so that's what you expect. Now, what happens if you now, in addition, now put the semiconductor into a magnetic field? Okay, so in this case, the magnetic field is represented by what you see here, the red arrow, with magnetic strength of B, okay, magnetic field strength of B. And this magnetic field is essentially, if you think about it, going into the screen, right? Which means that the north is outside the screen and the south is opposite the screen. So it goes from north to south. That's the direction of your magnetic field. Okay, this magnetic field arrow, right, basically points from north to south. Okay, so now if you have this magnetic field that is present, what will happen to your measurement across the top and bottom, 0.3 and 0.4? Okay, so when you put this semiconductor in the magnetic field, what you will find is that you actually would register a reading on your voltmeter now. Okay, you will start to find a reading. You get a reading. It's no longer 0 if you put it in a magnetic field. Okay, so the question, of course, is why is that so, right? So the reason for measuring now voltage difference is essentially because of this effect here called the resulting force, right, that comes about because of the presence of the magnetic field called the Lorentz force. And so this is arising from the interaction between the flowing charge, okay, with the presence of magnetic field. So if you have charged particle flowing through a magnetic field, you actually generate a force, the Lorentz force, that will push the charged particle in a certain direction. Okay, so the Lorentz force mathematically is defined as a cross product between the velocity of the carrier and the magnetic field. Okay, cross product, and multiplied by the charge of the carrier that you're analyzing. Okay, this force would be acted on the charge carrier, and this is the reason why you get a difference in the voltage. Okay, so just to give you some idea, right? If you have, okay, let's say magnetic field B is here. Okay, and then let's say the carrier, some carrier is moving in a direction that's perpendicular to B, right? Velocity V. Then if you do a cross product, V cross B, okay, the cross product itself will give you a vector that is perpendicular to both right? This is V. Have you guys learned cross product in vectors? Everybody know this, or something new to you? Yes. Okay. Okay. Anyway, just a quick recap for those who may not have this covered in your math yet. So if we do a cross product, right, V cross B, then it basically gives you a vector that's perpendicular to V and B, and the direction of this is given by the right-hand grip. Okay, so if you use your fingers, right, and you sort of grip from V to B, then your thumb is pointed upwards. Okay, so if you do a right-hand grip, you know, your finger is like that, right? Okay, that's your hand. Okay, so if you do a cross product, that means your other fingers, you move from V to B, then you find that your thumb points upward. Okay, so that's the direction of the cross product vector. Okay, so this cross product, okay, V cross B is upwards for the case of electrons, but you have to multiply by minus Q, right? So which means that the final force is actually downwards. So the Lorentz force for electron is actually downwards. Okay, this is for electron. On the other hand, for holes, right, if it's a hole, then V cross B vector is upwards. The charge is positive. So in the case of holes, the Lorentz force, given the same configuration, where the holes are moving in with a velocity of V in the same direction, then the Lorentz force for holes, it's actually in the same direction as the cross product. Okay, it's determined by the charge. All right, that's how the Lorentz force actually come about. I mean, the principle for this is the same as why you put current into a motor, the motor turns, right? Okay, it's the same effect. Okay, the current that's flowing in your coil in the motor are essentially electrons, and the electron cuts through the magnetic field, which then generates a force that will push the carrier and in turn, cause the coil to rotate, right? Okay, so how does this effect actually result in a charge forming between the top and bottom? So we consider holes in this case. Okay, we consider holes that is moving in a semiconductor because of the presence of the power source, right, the voltage source. The current flow from left to right, okay, which means that the hole, okay, this is the hole, right, H plus, moving from left to right. And if you do a cross product of velocity with magnetic field, you find that the Lorentz force is upwards. And you find that as the hole move from left to right, they get pushed upwards to the top surface. And you get accumulation of positive charge on the top surface of your semiconductor. Okay, so and conversely, the bottom will be more negative, right? And as a result of this accumulation of charge at the top, you get a voltage difference between 0.3 and 0.4. Okay, so this voltage that results is called the Hall voltage, and the resulting electric field, right? Okay, it's called the Hall field in the semiconductor. Okay, and the presence of this electric field, okay, because now it's positive at the top and negative at the bottom, this presence of electric field would tend to push away the holes. Okay, so you have now two competing forces, right? One is due to the Lorentz force that push the hole up, which result in the electric field, but the electric field that is formed, right, will push the hole down. So we have these two competing force, okay, due to Lorentz force and the electric force. And at steady state condition, okay, you find that this force that's acted on the hole, in this case, will be balanced. Okay, that means the total force that the hole will experience will be balanced. Okay, so the sum of the force that the whole experience will be equal to 0, right? So once it stabilizes, then the force that the whole experience will be stabilized and they just flow across directly without any subsequent movement anymore. Okay, so using this steady state condition, okay, we can actually relate the Hall field, right, to the drift velocity of the carrier and the magnetic field that's present in your semiconductor material. Okay, and in fact, the the force that the hole experience is dependent on the electric field. So it's the charge multiplied by the electric field. Okay, so with this, we can actually rearrange this expression. And we will find that the Hall field is given by the product of the drift velocity and the magnetic field of your experiment. Okay, and in fact, this drift velocity component here can be expressed in terms of the drift current density, because we know that the drift current density is given by Q multiplied by P multiplied by VdP, right, which is essentially the mobility of holes and the electric field, right? Okay, so we can make use of this drift current equation and write down VdP in terms of the drift current. Okay, so if we do that, you find that your Hall field is essentially given by the drift current density multiplied by the magnetic field and P, okay, the carrier concentration of holes in the semiconductor. So in this experiment, we have actually a parameter that's defined called the Hall coefficient, which is given by the ratio of the electric field with the drift current density and the magnetic field. Okay, that's called the Hall coefficient. And in fact, from this equation here, right, this Hall coefficient is simply just 1 over Q multiplied by P. Okay, so what it means is that if you can determine the Hall coefficient from this group of terms here, if I know this value, right, I can effectively find out what's the hole concentration in your semiconductor. Then the question is, do you know this parameter? Actually, we know this parameter, right? Because from the experiment itself, right, we will know this value, EH, because we can use the multimeter to measure the voltage across the top and bottom. Okay, so if you divide that by the distance between the top and bottom, you would know your EH, okay? And this drift current is the current component in the horizontal direction, which again, from your measurement setup, you will be able to measure the current that's flowing in the circuit. If you know the dimension of the semiconductor, it's it'll basically allow you to calculate the current density, which is the current that's flowing divided by the cross-sectional area of your semiconductor. Okay, so drift current density is also something that we can measure experimentally. And the same goes for the magnetic field, right? It's also something that you can measure. There's an instrument that you can use to measure it. So all these parameters are actually quantity that you can measure. So if you can measure and determine these parameters, I can effectively find out what's the concentration in your semiconductor. Okay, so you see that from this experiment, we can determine concentration of carrier in the semiconductor. So that's one thing that you can determine, right? Okay, so this is the parameter that we're talking about. Okay, all these things are quantity that you can actually measure and calculate from your experiment. Okay, so you can find out carrier concentration in the semiconductor. Now, if you look at the case of N-type semiconductor, the reasoning is the same. So in this case, if you maintain the same experimental condition, right, where the current still flow from left to right, then you find that in this case, if let's say this is an N-type semiconductor where electron is the majority carrier, then the majority carrier electrons would tend to move to the left. Okay, because electron move in opposite direction to conventional current. So if the electron move to the left and you work out the Lorentz force, you will find that the Lorentz force actually would basically push the electron upward as well. Okay, so if you work through the direction, right, you'll find that the Lorentz force is pushing the carrier up. And in this case, you find that the top part actually become negatively charged compared to the bottom part. And you will still measure a voltage difference, but in this case, the voltage difference that you measure will be opposite sign to that of the N-type semiconductor, where holes are the majority carrier. Okay, if we refer back to the few slides, right, the hole one, the top is positive. Okay, N-type, you actually get top negative. So you basically register a difference in the sign or the polarity of your measurement. Okay, so this actually gives us also a very useful method to tell whether the majority carrier in the semiconductor is electrons or holes. Okay, because if you remember, right, the measurement configuration is the same. right? The setup here is exactly the same. Only difference is that we use N-type here. The previous one is a P-type. And you see that given the same experimental configuration, the difference in the readings, right, is actually in the sign of the Hall voltage. Okay, so the sign actually will tell you whether you're dealing as an N-type semiconductor or you're dealing with a P-type semiconductor. Okay, so this is actually the other thing that the Hall effect measurement can tell you, whether your material is an N-type or P-type. Okay. So similarly, if you go through the analysis, right, you can also work out a Hall coefficient in this case, which can be determined based on the parameters that you measure, and it relates to your concentration of majority carrier electron in this case, right? And similarly, you can find out what's the electron concentration in the semiconductor material. Okay, and at the same time, we can also find out mobility, because if you go through the discussion, right, you'll find that the mobility is actually related to the Hall coefficient and the conductivity of your semiconductor material. Okay, which means that if you know your Hall coefficient and the conductivity, we can effectively work out the mobility of your carriers as well. Okay, so this Hall coefficient, as I mentioned before, is something that you can determine from an experiment, right? Because it's based on quantity you can measure. And in fact, similarly for this conductivity, right, this conductivity term here is also something that we can determine from the experiment, okay, by this expression here, which is effectively your Ohm's law, right? Okay, so using the Ohm's law expression, we can actually find out conductivity, because this is based on quantity that you can measure in the experiment. Okay, the V naught over the I, which is something you can measure in the experiment, and this ratio of the dimension are also quantity you can measure, right? You can measure the size of the semiconductor material. And by measuring that, we can also work out the mobility of your carriers. Okay, so you see that the Hall effect measurement doesn't just give you one parameter of the semiconductor. In fact, it tells you 3 different things about the semiconductor. Okay, ranging from the type of semiconductor you are dealing with, the majority carrier concentration, and the majority carrier mobility in the semiconductor. Okay, so this is actually a very versatile experiment that allows you to determine several things. And this is one of the experiments that we'll be doing in lab 2 exercise. Okay, when we come for lab 2. Okay, another experimental technique that you will be using as well in lab 2 is the 4-point probe measurement. Okay, so the 4-point probe measurement is basically a measurement technique that is used to quantify the resistivity of semiconductor material. Okay, it's commonly used in semiconductor industry. And this basically involves using 4 contact points on your semiconductor to determine effectively resistance in the semiconductor. So the immediate question that you may ask is, why do you need 4 probes on the semiconductor, right? Because if you think about it logically, you would have thought that to measure resistance, you could have just have 2 probes, right, making contact with your semiconductor. So the semiconductor is here, right? Okay, so we use 2 probes, and you touch the surface of the semiconductor, and you connect this to perhaps a current source. You pump some current I, okay, to the semiconductor they are making contact with, and then you measure the voltage across the 2 contacts. Okay, so if you have current, you have voltage, you can actually find resistance. If you know the resistance, you can determine the resistivity of the semiconductor, right? Okay, this probably will be something that is quite straightforward, that you think would work, okay? But unfortunately, this approach has some problem, in the sense that because the semiconductor material that you measure, right, typically semiconductor, when it's doped, the resistivity is very low, okay? So what you find is that when you measure the resistance using this method, okay, using the conventional method where you just put a probe directly on the semiconductor and put a current and measure voltage, right? What you find is that you actually will be measuring some undesirable resistance, okay, that will appear in the circuit. Okay, the first is what we call a contact resistance, right? Okay, which is the point where you make contact with the surface, right? If there's some imperfection, then you get some resistive effect at that point as well. Okay, so there's some resistance that you get here, right? Okay, so that's one resistant component, okay, that will creep into your measurement. And another unwanted resistance that will creep in is what we call a spreading resistance, okay, which is kind of this portion here, right? Because as the current get into the semiconductor, the current basically would spread out, right, before it becomes sort of linear or in parallel to the semiconductor. So what you really want to measure is this parallel components, right, where the current flow parallel to one another through the material. Then that gives you a true indication of the resistivity. Now this part here, you have the carrier essentially moving with different distance, right? And obviously you would know that the one that goes through a longer distance will experience larger resistance compared to the ones that is going through the short distance, okay? So overall, the resistive effect here will be high, okay? It will be high. So, okay, so bottom line is that, in this measurement approach, you get this contact resistance, you get a spreading resistance, right? And you get, of course, the real resistance that you're trying to measure. Okay, the real resistance you're trying to measure will be in the middle part here, okay? So it will not be a problem if the resistance of your semiconductor is high. That means if this value is very large, then these two components here will be not an issue, right? You'll be negligible. But a lot of times semiconductors, as I say, when you dope it, the resistance is not very high. So which means that this part here, right, this the true resistance that I'm trying to measure is actually pretty small. Okay, so this component that I'm trying to measure is actually very small compared to the rest. So as a result, when you measure the resistivity of your semiconductor using this method, right, you actually get this significant component that comes in. So what you're measuring will be dominated by this unwanted resistance, okay, the contact resistance and spreading resistance. And as a result, it's not a true measurement of the real resistance of your semiconductor. So how can we overcome this constraint then? The alternative method is actually quite elegant, okay, using this 4-point probe experiment where instead of 2 probes, we use 4 probes to make contact with the semiconductor. The outer 2 probes, we basically inject current, okay, to the outer 2 probes. So the current will basically get into the semiconductor, and then you go horizontally, right, to the other side. And the middle 2 probes, we basically connect to a voltmeter and we make contact with the surface of the semiconductor. And we measure the voltage drop across the semiconductor. So you can see now with the voltmeter that's connected to the middle probe, okay, it doesn't draw current from the semiconductor, right? Because it's just a voltmeter that's applied to the semiconductor. So if it doesn't draw current, you will not measure the contact resistance, okay, for the middle 2 probes. And you also will not measure the spreading resistance because the spreading effect is now constrained to the outer part, outer probes, okay, because the outer probes is the one that is injecting current. So the spreading resistance effect is on the outer portion. Okay, so once the current get into the middle portion where you are measuring with the voltmeter, okay, the middle portion here where you're measuring with the voltmeter, the spreading effect is not there anymore. Okay, the spreading is only where you make contact and you're injecting the current. Okay, so this basically effectively remove the effect of contact resistance and spreading resistance. Okay, and with the current that you inject and the voltage that you measure in the middle probe, you can determine the resistivity. All right, so it's just a simple resistance measurement technique, just that we make use of this 4-point probe configuration to overcome this contact resistance and spraying resistance that creeps in if you use the conventional 2-prime method to measure resistance. Okay, so it's effectively a resistance measurement technique. Of course, the resistivity calculation, depending on what is the separation between the probes, right? There's actually different equations that you can use. Okay, so we can read through. In terms of the experiment that we're using in lab 2, okay, the condition will meet this one here, okay, where the wafer thickness D, okay, the wafer thickness is small, right, compared to S naught. S naught is the spacing between the probes. Okay, so if D is small compared to S naught, then the equation that we can use is this. Okay, so it's a ratio of the voltage that you measure divided by the current that you inject, multiplied by the thickness of the wafer, and multiplied by this constant 4.53. Okay, so that's the formula that you're going to apply in the lab. Anyway, the lab manual has this all documented in it. Okay, so this one is just measuring the voltage, measuring the current, and just do the calculation. All right. And okay, just for your information, right, in semiconductor, a lot of times we use a quantity called sheet resistance, okay, which is the ratio of the resistivity versus the thickness of your semiconductor wafer. Okay, so from this resistivity equation that you see here, right, if you do that, then you find that the sheet resistivity, right, or sheet resistance is simply 4.53 multiplied by V over I. Okay, so this is kind of like a normalized resistance that is defined to allow like quick calculation of resistance in semiconductor material. Okay, just be aware that there's this term that's used as well, and the unit for this is actually this unit here, ohm per square. Okay, so ohm per square. Okay, that's a quantity that we use quite frequently. Okay, just appreciate that it's there. Okay, don't worry about the actual use. If you do specialize in this, you'll see more of this. Okay, so yeah. So in fact, once you determine the resistivity, a lot of times for many semiconductor material, right, there is actually this calibration graph or calibration graph that you can find or use to determine the doping concentration in the material. Okay, for example, silicon, you basically have these two graphs, right, depending on whether it's N or P type. So you measure the resistivity, then from the calibration graph, you can determine the corresponding doping concentration of the carriers. Okay, so in fact, in the lab 2 experiment, this is also what you're going to do. After you calculate the resistivity, you can then work out the concentration of the impurity carriers in the semiconductor, the doping, okay, using the calibration graphs. All right. Okay, so these are the two characterization technique that we'll be using in lab 2. Okay, so just go through this again before the lab experiment, before you come, okay, so that you understand what you'll be doing. Okay, so perhaps let's go for a 10 minutes break, and then we'll come back in 10 minutes time to finish the other half of the discussion. Okay, let's go for a 10 minutes break. Come back at 5:30. Okay, let's get back to our discussion. Okay, the next topic that I will touch on is the non-equilibrium excess carrier in semiconductor materials. Okay, so that will be the last topic that we'll be covering for today's discussion and the discussion for next week. And after next week, Prof. Ang will take over and he would talk about the semiconductor devices, all right? Particularly the PN junctions and detectors, LEDs, all right? Okay, so this non-equilibrium excess carrier condition in a semiconductor is important because when you operate a semiconductor device, you basically will introduce non-equilibrium condition, right? Because you either apply a voltage or you shine light on the device, and then that would basically create changes in the carrier concentration in the semiconductor. So the question is, how would these extra carriers behave in those devices? Understanding it is important because then it allows us to understand how the current would change in these devices. Okay, so there will be two non-equilibrium excess carrier conditions that we'll be talking about. The first will be due to optical illumination. That means you shine light on the semiconductor, right? What's going to happen to the carrier concentration in this semiconductor? So for this optical illumination case, right, the scenario is essentially this. Suppose I have a semiconductor material, and let's say I shine light uniformly everywhere, okay, on the semiconductor material. Okay, so if you do that, the question we ask here is, what is the excess carrier that is created in the semiconductor? That means the delta N and delta P. Okay, the extra carriers that's created in the semiconductor material. So here we are going to analyze this as a function of time, right? So these quantities will be discussed as a function of time because if you look at the scenario here, right, we're basically illuminating the semiconductor uniformly. So in terms of changes respect to position, there's zero. Okay, there's no change. It's the same everywhere. So the only thing that will change is respect to time. Okay, everywhere, every X position, any X position, the change is the same. Okay, because we are illuminating it uniformly. Okay, so the thing that we're trying to find out is how the excess carrier varies with time. Okay, that's the first non-equilibrium condition that we'll be talking about. The next one, okay, that we'll be talking about is based on external bias. Okay, if you apply a voltage, for example, to a semiconductor, you would basically get a condition where carriers are injected into the semiconductor, right? So this carriers that's injected will be in excess of what's already present in the semiconductor. So the question is how much current would be produced, okay? And for this particular scenario here, the specific condition that we're looking at, right, is this. Okay, so for a piece of semiconductor, if you have an external bias, okay, let's say I inject carriers at one end of the semiconductor. Okay, so if we do that, then you're going to introduce a lot of, this extra carriers at the edge. And because of this high concentration of the extra carriers, right, compared to the others, these guys will basically start to diffuse into the semiconductor, right? And as they diffuse, these carriers will also recombine as they get deeper and deeper into the semiconductor. So what we're interested to find out here is how does your excess carrier, whether it's delta N or delta P, depending on what you inject, okay, how does it change with position in the semiconductor? Okay, so for this second non-equilibrium condition, specifically, we're interested to know how the concentration varies with position into the semiconductor. Okay, so you see a difference here. The first non-equilibrium condition relates to how the excess carrier change with time. The second one relates to how it changes with position in the semiconductor. Okay, so this is the two non-equilibrium situation that we're going to discuss. So what you'll find is that under non-equilibrium condition, okay, the extra carriers that are produced, right, they are transport parameters. Okay, the way they diffuse, the way they drift, would follow that of the minority carrier in the semiconductor. Okay, and the two carriers that are created, they basically will move similarly, and this the transport parameter that they will have, right, will follow that of the minority carriers in the semiconductor. And under this analysis that we're going to do, okay, there's also a basic assumption that we will make. Okay, the first is that your majority carrier concentration is significantly larger than that of the minority carrier concentration. Okay, there's actually these two assumptions that we will make as well, okay, to simplify the discussion. Okay, so the first one is majority carrier is larger than the minority carrier concentrations. Okay, that's first assumption. The second assumption is that the non-equilibrium condition is what we call a low-level injection condition. Okay, meaning that the extra carrier that we introduced into the semiconductor is significantly less than the majority carrier concentration. Okay, so under these two assumptions, then you find that the analysis is a lot simpler, and we can actually get analytical expression that we can use. Okay, so bear in mind these two assumptions that we're going to, in fact, make as we go along when we do the derivations. So as an example, right, suppose I have a p-type semiconductor, and let's say the two assumptions that we mentioned are satisfied. Okay, that is your majority carrier concentration, P0 in this case, is much greater than N0, and your extra carriers, delta N, delta P, is significantly less than your majority carrier, so P0 in this case. Then you find that this extra carrier that is in the semiconductor, right, the way they behave, the movement, will basically follow that of the minority carrier in the semiconductor. That means, they'll take on the transport parameters of the minority electrons in the semiconductor. Okay, so what governs their movement will be the electron parameters. All right. Okay, so just keep this in mind. Right. So of course, previously we talked about equilibrium condition where in a semiconductor, they're sitting there, right? Then we see that there is actually these two mechanisms that creates or cancel out the carriers in the semiconductor, the generation and the recombination process. So this is always there, regardless of whether you have any external influence or not. Okay, whether you have electric field or whether you put it in a different temperature, these two mechanisms is always there. Okay, you have a generation produced due to the thermal effects of temperature, and the recombination process, again, that's a natural process that the carrier would tend to always recombine. Okay, because if they see one another, then there's a chance that they'll recombine. All right, so this is always there. And we mentioned that under thermal equilibrium condition, the thermal generation rate, okay, that means the number of carriers that is generated per unit volume per unit time, will be equal to the recombination rate. That means the number of electrons and holes that is cancelled out per unit volume per unit time will be the same. Okay, so there's no net change to the electrons and holes in the semiconductor under thermal equilibrium condition. So in fact, the recombination rate, okay, assuming that there is just purely due to band-to-band transitions, right? The recombination rate is simply proportional to the product of the electron and hole concentration in a semiconductor. Okay, with a constant of proportionality, alpha r here. So this is a parameter that is material dependent. Okay, so if I have the recombination rate in a semiconductor is solely determined by the number of free electrons and number of free holes that you have in the semiconductor, which in a way makes sense, right? Because if you have a larger number of either one of these, then the chance of having a recombination will be higher. Okay, if there's more electrons, then more of them will be able to meet the holes and they will recombine. Okay, so you find that the rate will increase. Okay, so this is something that should be expected. Now, under thermal equilibrium condition, if your thermal generation rate is equal to the recombination rate, then we can write down this expression here, GTH equal to R, which is alpha R MP. And because we are dealing with thermal equilibrium condition, the N and P here is essentially the N naught and P naught. Okay, so this N and P is whatever the concentration of the carrier is, okay, at the particular situation that you're analyzing. So in the case of thermal equilibrium, then this N and P is simply just N naught and P naught. And if you put that in, then you see that we have an N naught and P naught, which based on mass action law is simply Ni square, right? So from here we can see that the GTH, the thermal generation rate, is simply just alpha R Ni square. So the thermal generation is dependent on the intrinsic carrier concentration, N, right? If you recall, right, the Ni we have also derived, and we show that this is actually related to the exponential of minus Eg over kBT. Okay, so there's an exponential dependence on temperature and band gap. Okay, so fundamentally this thermal process, thermal generation rate, is dependent on band gap and the temperature, which again is not surprising, because how many get generated depends on how much temperature you have, right? The higher the temperature, you expect more to be generated because the thermal energy that's available is higher. Right, that will also affect your generation rate, because if your band gap is smaller, for example, then the rate at which carrier can go up will be higher as well, because the barrier is smaller. Okay, so this qualitatively agree with what you expect, okay, for thermal generation rate. So thermal generation rate simply is just dependent on the band gap and the temperature of the semiconductor material. Okay, and this is in fact kind of independent, of the doping type in the semiconductor, right? Because in this expression we do not have the doping effect here. It's just Ni, so there's the intrinsic behavior of your semiconductor. So if you consider the case where you have a semiconductor that has optical illumination now, right? So initially, let's say I have a semiconductor with concentration of hole as P naught and concentration of electrons as N naught. If I shine light on this semiconductor now, then this light illumination would basically promote extra electrons and holes to the conduction band. Okay, so it will introduce additional carriers, delta N, delta P. Okay, so this extra one is on top of the thermal equilibrium quantities. Okay, and in this case, because it's optical illumination, the delta N, delta P must be the same, because it's due to band-to-band transitions, and you expect the electron and hole number, the extra ones, to be the same. Right? For every electron that's promoted, you always get a hole that is created. Okay, so in this case, the delta N, delta P is equal because of the optical illumination. Okay. So in fact, with this optical illumination, your electron and hole concentration now is changed, right? Instead of just being N naught at thermal equilibrium condition, your concentration of electrons now is N naught, the thermal equilibrium component, plus the extra one that are created. Okay, so the N now we write it as N without the N naught to specify that it's a non-equilibrium condition. Okay, so similarly for the P, right, it's made out of two components now, the thermal equilibrium part and the extra carrier part, delta P naught plus delta P. Okay, so now we have a different delta N, delta P, and in fact in this case, right, in this case, you find that the product of electron and hole, okay, MP, is no longer equals to Ni square. So you cannot apply mass action law anymore when it's in non-equilibrium condition. Okay, the mass action law only applies under thermal equilibrium condition. Okay, so the N and P is no longer equals to Ni square, right? Because you have extra delta N delta P in your expression. Okay, so that's something to keep in mind. Right, so how do we describe this change in the carrier concentration, in a semiconductor in a general sense? Okay, so we describe the change in the concentration of carriers in the semiconductor using this expression here called the rate equations, right? So in this case, let us first consider the case of a p-type semiconductor. Okay, and if you assume that the majority carrier is much greater than the minority carrier, then the minority carrier electrons, okay, will generally be the carrier that we'll be analyzing. Okay, so how do we describe how the carriers are changing in the semiconductor? Okay, you can write down this rate equation, which describes how n changes with time. So dn dt, right? How generation process, right? Okay, so this is the generation process that adds on carrier, okay, that increase the electron concentration. Okay, so this add to the electron concentration with respect to time. And of course, we have the recombination process, okay, which subtract, right? This basically reduce the carriers in the semiconductor. Okay, so in a semiconductor, you essentially have this generation process that would increase the number of electrons and holes. And of course, you also have this intrinsic process that cancel out the electrons and holes. So the net difference, right? The net difference between generation and recombination will tell you how the N is changing with time, right? Okay. So as an analogy, right? As an analogy, for example, you can think of this dn dt as let's say how much money you have, right, in your bank, in a bank account, okay, respect to time. And let's say the generation rate, will be the process that adds the, your money, right? So suppose your parents give you money, right? Let's say your parents give you, for example, just for sake of discussion, 500 per month, right? Okay, and the recombination rate will be the, the rate at which you spend it per month. Let's say you spend 200 per month, then the net change in the money in your bank account will be 500 minus 200. So every month, if you keep at this rate, then every month the amount of money that you have will be increasing by 300 per month. Okay, so similarly, in the case of semiconductor, this is the equation that you can use to describe how the carrier number changes, okay, due to this different source. So in terms of the generation rate, we talk about the intrinsic one, which is due to thermal effects, the thermal generation. Okay, this would basically add on the number of electrons in the semiconductor, right, the GTH. And in fact, if you shine light on the semiconductor, that also produce additional electrons in the semiconductor and holes, right? Okay, so there's also another process which is the optical generation. So the overall generation rate that you can find in a semiconductor will be the thermal generation and the optical illumination. Okay, the thermal excitation or the optical excitation. Okay, and so we put that into the equation. Then our rate equation is simply written as dn dt equals to GTH plus GL. That's the generation rate, and the recombination rate, the process that reduces the number is just one. It's a recombination, so it's just R minus R. Okay, so we can make use of this rate equation to basically derive how the carrier concentration will change in the semiconductor with respect to time. Okay, for the scenario that I mentioned just now. Okay, so for the scenario that I talked about just now, right, which is if you have a piece of semiconductor and you shine light uniformly everywhere. Okay, remember I said that the thing that we're interested in here is how your delta N or delta P, depending on which one you're analyzing, basically change with time, right? Okay, so we're interested to know how this delta N, delta P change with time. So under this scenario, there's going to be 3 cases that we'll be analyzing. The first is a trivial case, thermal equilibrium condition, where there's no external influence, right? That means no optical excitation, just semiconductor sitting there, okay, in equilibrium. Then the second condition is the steady state condition, where you shine light on a semiconductor and you kind of let it stabilizes. Okay, then how would your delta N, delta P look like? Okay, then the last one is how does delta N, delta T, delta P, okay, behave when you suddenly switch off the light to the semiconductor? Okay, so the result is, in fact, kind of summarized here just to give you an overview, right? Okay, this is what we're going to discuss and derive. So this initial portion here, right, this first portion here is when there's no optical illumination. That means the semiconductor is in thermal equilibrium. So this is actually a trivial case. If there's no external excitation, then you expect the electron concentration to stay at the thermal equilibrium value, which is N0 in this case, right? So it stays flat at N0. And let's say at some time here, right? Sometime here, I switch on the light on the semiconductor, then you have extra carriers that's been created. Okay, so you expect the carriers to increase in numbers up to a stage where it will stabilize. Okay, so this part that it stabilizes is the one that we're going to analyze. Okay, that's the case 2, right? Okay, what is this extra carrier that is present here? Okay, so in other words, we're trying to find out what is this delta N. Okay, so that's case 2, right? Case 1, as I say, is a trivial case, is this portion here. Then case 3 is after the steady state condition, if you switch off the light, then the optical excitation source is gone, right? You take out this extra generation process, and you would expect the extra carrier to slowly decay back to 0, and you go back to your thermal equilibrium concentration for N0. Okay, so this is our case 3. And here, similarly, we're interested to find out what is delta N, which will not be a constant anymore, right? Because from the graph here, you can see that it's changing with time. So we're trying to find out what is delta N as a function of time. Okay, so in this case, the excess carrier do not vary with position because the light that's shining on a semiconductor is assumed to be uniform, right? We shine everywhere uniformly. Okay, so that's what we're going to derive in our subsequent discussions. Okay, let's look at the thermal equilibrium case. This is actually trivial. In fact, in the previous case, we have actually sort of analyzed this already. So it's in any case still instructive to just go through this so that you see how the rate equation can be applied to analyze this condition. So at thermal equilibrium condition, we know that you will not expect a change in the electron concentration with respect to time, right? Because it's thermal equilibrium, so everything is constant. So your dN dt is actually equal to 0, right? So dN dt is 0. And because it's thermal equilibrium, there's no external excitation, right? So the GL is also 0. That being the case, your dN dt is 0, this component is gone, this component is gone. Then what you're left with is just GTH equals to R, right? Okay, so the rate equation reduces to GTH equal to R, which is what we know already, right? And from our previous discussion, we see that GTH is just alpha R Ni square. So this thermal generation process is just dependent on the intrinsic property of the semiconductor, that is the band gap and the temperature of the semiconductor. Okay, so that's the trivial case. Okay, let's look at the case 2, where when you shine light on a semiconductor and you give it sufficient time, right, and it stabilizes, okay, how would the delta N end up, okay, in terms of its value? So again, using the rate equation at steady state condition, right, the graph that we showed, right, steady state means that the concentration of the carriers don't change anymore. Okay, that's why it's flat. So under this steady state condition, we can similarly write down dN dt equals to 0. You're not expecting the carrier concentration to change with time anymore. Okay, so if you set dN dt equals to 0, then you have GTH plus GL minus R equals 0. And GL in this case is non-zero, right? Because you have optical illumination, you have light shining on the semiconductor. So if you rearrange this, we can write GL as minus bracket GTH minus R. And we can actually put in the respective terms for GTH and R. So recall GTH just now using the trivial condition, right? We see that it's equal to alpha R Ni square, independent of the external factors. Okay, just dependent on the intrinsic characteristics of the semiconductor. And this R is alpha NP, right? And N in this case is no longer just N naught. Okay, because now you have excess carrier, so it's N naught plus delta N. And this P here is P naught plus delta P. Okay, so if you put all this in, okay, if you follow the derivation, right, you put all this thing in and you multiply out the terms, then you have for the NP, right, the product of the NP, you actually have a total of 4 terms, one of which is N naught P naught, which is essentially your Ni square. Okay, so we can actually cancel out this term with the Ni square from GTH. And that leaves us a total of 3 terms in your GL expression. Okay, there's 3 terms there. And if you take out the common factors, alpha R and delta N, okay, knowing that your delta N, delta P is really the same, so this is really delta N. If you replace the delta P with delta N, then you have alpha R. We take out the delta N as a common factor. Then what you have in the bracket now is N naught, P naught, and delta N. Okay, so we can actually reduce this expression a little bit further, okay, using the 2 assumptions that we talked about earlier, right? If you recall, the 2 assumptions that we mentioned is that majority carrier is much greater than the minority carrier. That means P naught is greater than N naught in this case. All right, so given this condition, then the N naught will be negligible. And the other assumption is that you're dealing with a low level injection condition. That means the excess carrier is less than the majority carrier concentration. So delta N is significantly smaller than P naught. So in the bracket terms, right, this delta N will also be negligible. And that leaves us just 1 term to deal with. Okay, so this assumption essentially allows us to reduce the expression, right, to GL equals to alpha R P naught delta N. And we actually can define this alpha R P naught as a quantity called 1 over tau N naught, right? Okay, this tau N naught is a parameter called the excess minority carrier lifetime. And this is a quantity that describes how long excess carrier would exist in the semiconductor. Okay, because if you think about it, these extra carriers, right, that's in the semiconductor, because they're extra, okay, so they will tend to want to recombine, right? So the time that this extra carrier can sort of exist before they start to recombine is the excess minority carrier lifetime. Okay, so it's kind of like the average time that the minority carrier can exist in the semiconductor before it recombines. Okay, so the GL now is reduced to this quantity, delta N, over the excess minority carrier lifetime, tau N naught. Okay, where the tau N naught is in fact determined by the majority carrier. So the higher the concentration of the majority carrier, the smaller the excess minority carrier lifetime. Which again is not surprising because the more majority carrier there are, right, the shorter the lifespan of the minority carrier, because the chance of them encountering a majority carrier is higher if there's more of them, and they'll tend to recombine earlier. Okay, so you expect there to be an inverse relation between the excess minority carrier lifetime and the concentration of the majority carrier. Okay, so that basically gives us now this form, right? Okay, where GL, right, GL is equals to delta N over tau N naught, which means that if you rearrange, remember what was our starting objective is to actually try to find out what's the delta N, right? The constant delta N value when you are in the steady state condition. Okay, so the delta N is simply equals to GL, the optical generation rate, multiplied by the minority carrier lifetime, tau N naught. Okay, so this tau N naught is essentially a material property as well. Okay, different materials will have different minority carrier lifetime. Okay, and these are parameters that it's measured, it's characterized before. So usually you can find this in reference books or reference materials. Okay, so these are actually well characterized material parameters. So if you know your optical generation rate, then you can actually find out your excess carrier concentration under steady state condition. All right. So similarly, you can do the same analysis for N-type semiconductor. Again, using the same assumptions that we talked about, right? You can similarly derive the expression for delta P, right? So from this delta P expression, you find that the delta P will have the same form as the electron one. Is given by the product of the optical generation rate and the excess minority carrier lifetime. Okay, tau P naught in this case. Okay, so you can similarly calculate the delta P using this expression if these two conditions are valid. Okay, so the important thing here is that these two assumptions that we talk about must be valid. Then you can make use of these expressions, okay, to work out the excess carrier concentrations. All right. So in summary, under this case 2 condition, right, where you shine light on a semiconductor until it reaches steady state condition, the excess carriers in the semiconductor, right, whether it's in the P or N type, is given by the product of the optical generation rate and the excess carrier, right, which is the excess minority carrier lifetime in the semiconductor. So for P type, you would use the minority electron lifetime. For the N type, you find the parameter is that of the minority holes in the semiconductor. Okay, so remember this is only applicable, right, is if the two assumptions are valid, right? So that's requiring the assumptions, okay, to be valid. Okay, so strictly speaking, if the assumptions are not valid, then you actually cannot use these two expressions. You have to go back to a rate equation and derive from scratch again, okay, to find out what's the actual expression. Ken? Anyone has any questions on this?
Hi, Professor.
Yeah.
May I ask how do you equate the generation rate due to illumination with the excess minority carrier lifetime?
How to equate?
Last slide, previous slide. This one.
Okay.
The top equation.
The top equation, okay.
How do you equate the first term with the last term?
How do you equate the first to the last?
Yeah.
You mean how you get from here to here?
Yeah.
Okay, so from the assumption, we get GL equals to alpha R P naught N naught, right?
Yes.
Okay, then this alpha R P naught is in fact the reciprocal of your minority carrier lifetime.
How is it so?
Well, it's a parameter that is yeah, it's okay. The way you can think about this is if you look at the units, probably the units is a easier way to understand. Okay, if you look at the generation rate, what is the unit of the generation rate? Is the number that is generated per unit volume per unit time, right?
Yes.
Correct.
Yes.
And what is our unit of delta n? Unit of delta n is essentially excess carrier concentration, so it's number per unit volume, correct?
Yes. Yes.
Which means that the product of these two terms must be in units or per unit time, right, to be compatible with this quantity on the right. So if this is a quantity that's per unit time, that means it's kind of like a reciprocal of time, okay, which is this time here, right? This reciprocal of alpha RP naught is a time quantity. And this time quantity is defined as the excess minority carrier lifetime. That means how long they exist before they actually recombine in the semiconductor.
But what is the physical meaning behind this equation? Does it mean that the rate at which excess minority carrier is generated equal to rate at which it is decreasing?
No. This excess minority carrier lifetime essentially describes on average, right? On average, how long it takes for this extra carrier to sort of exist before it recombines and disappear. So it's a time quantity that defines the average time that a minority carrier exists in the semiconductor.
Oh, okay.
Yeah.
I mean, I understand the dimensional analysis of this equation, but the physical meaning is quite hard to understand.
Yeah, the way you can think about it is that because your GL is essentially external process, right, which produce extra carriers. So this extra carrier that is there, so if you apply a GL and then you remove the GL, then you have this extra carrier that's created, and this extra carrier will not be there forever, right? After some time, they actually will recombine. So the average time that they are there before they recombine is kind of quantified by this term here.
Okay.
Yeah, and I think when we talk about case 3, then it may become clearer to you.
Okay.
Okay, but at this stage, you understand, right, why the alpha RP naught is inverse time. It's a reciprocal of time. Yeah. So it's an inverse time quantity.
Okay.
Yeah. So later on, I think when we talk about case 3, then it'll probably be clearer to you.
Okay.
In terms of the actual mechanism behind this.
Yeah.
Okay.
Yeah.
Yeah. Any other questions?
Hi, Prof.
Yeah.
For the Hall effect measurement, right? It says that we can find the majority carrier concentration and the majority carrier mobility.
Yes.
For the majority carrier mobility, earlier on it says that the mobility obtained from equation Z11 is called the Hall mobility and is different from the conductivity type measurements. What does this mean?
Yeah. Okay, the conductivity measurement is essentially the one where you do like a resistance measurement, right? So in fact, from the 4-point probe experiment, other than finding the resistivity and the concentration of the majority carrier, right? In fact, this experiment, we can also find out the mobility of the carriers. Okay, because this effectively is applying a voltage, then you have current flow, right? So what you're measuring here is the drift current. So if you can find the resistivity, you can find the concentration, you can also find out the mobility, because you know the voltage and you know the current that's flowing. Okay, so effectively you can practically find out the mobility as well. Okay, so this measurement, in fact, would also give you the mobility. This mobility that you determine from such measurement, right, will be different from that. A little bit could be different from Hall measurement, because you find that the magnetic field, the presence of magnetic field, can also have some effect on the mobility. So it can change its behavior a little bit, So usually we distinguish this from the conductivity type measurement by calling this the Hall mobility. So that you're aware that it's determined from a different characterization method, which may deviate from the conductivity measurement because of the presence of magnetic field.
Okay, so the majority carrier mobility refers to the Hall mobility in this case.
Yeah, if you measure it with the Hall measurement method.
Okay. Sorry, another question, right? Is that for the majority carrier concentration, is it determined from the JN drift?
You mean for Hall effect measurement?
Yeah, because it says that we can find the majority carrier concentration.
Yes. So it can be determined essentially from the Hall coefficient.
So the Hall coefficient, which would give us JN drift, which will hence give us the...
No. So first you can find what's the Hall coefficient using this expression, right? Because the Hall field can be measured, right? Because we basically measure the voltage between the top and bottom. If you know the voltage, you know the size of the semiconductor, right? You can find out the electric field, which is just the voltage over the size, right? So this electric field here is something that you can measure. And similarly, this drift current density is the drift current density in the horizontal direction, which again, if you know the current that's flowing, you know the cross-sectional area of the semiconductor sample, you can find out the drift current density, okay? And the last parameter, magnetic field, right, is also something you can measure. Okay, that's actually an instrument that you will use in the lab too to measure the magnetic field. Okay, so all this quantity can be determined in the experiment, which means that you can use this parameter to calculate the Hall coefficient, right? Okay, so if you can calculate the Hall coefficient from our discussion here, right, you find that Hall coefficient is also equal to 1 over QP. So if you know Hall coefficient now, then you can use this to also work out the concentration of the majority carrier.
Oh, okay. I understand.
So they're all related.
Okay, thanks.
Yeah. Any other questions?
Hi, so can I ask if the recombination rate is affected by temperature?
Sorry, say that again.
Like, is the recombination rate affected by like external excitation or difference in temperature?
The recombination rate, no. The recombination rate will be solely determined by the concentration of electrons and holes. But of course, whether it's going to be affected by temperature, it's through the concentration. So, of course, if you say that you put the semiconductor at a different temperature now, right? And then the question is depending on how the increased temperature would change your N and P, right? So it would affect it through those parameters.
Oh, okay. Because the equation, there's one equation about like the thermal equilibrium is equal to.
Yeah.
Like for that equation, I was wondering, so the R is just constant.
Yes. The alpha R is a constant of proportionality. So this is a material parameter. So different material, different carrier, or rather different material, it will have its own constant value, alpha R. So alpha R is fixed for a given material.
Okay.
Yeah.
Thank you.
Yeah. Any other questions?
Hi, Prof. There's
Yeah.
one more question about the. I have one more question about the 4-point contact. Over there, there's two equations. One that says that if its thickness is less than 5s0, 5s naught, sorry, the multiplicative correction factor is needed. But
yes.
another equation is where d is small compared to s naught. So, what is considered small? Because small can also be less than 5s naught.
Yeah. So in a way, you can think of it as when it's 5s naught, you get this, right? Then if it is sufficiently small, then this kind of approximate to these values here. Small as in significantly smaller. But in any case, for the experiment that you're doing, right, the size of the wafer is actually satisfying this last condition here. Okay, so you would use this equation for the calculation. Yeah, so in fact there's you can also derive it. It's just that I did not cover that, which is not really essential. That's why I didn't talk about it. But if you actually go through the derivation, you can see how it results in these different equations here. Okay, so for this part here, I guess what we need you to know, or rather appreciate, is that under different dimension condition, right, then you need to use different equations, okay, to relate resistivity to the voltage and current that you measure.
Okay, sure. Thanks.
Yeah.
For the Hall coefficient equation, right?
Yes.
Is it necessary to only use JP drift?
Is it only necessary to use what do you mean?
Sorry, you can only use JP drift, right?
What is the alternative?
JN drift.
Okay. I see. So this depends on what type of semiconductor it is. So for this particular discussion here, we're looking at p-type. So the majority carrier in this case that is drifting, right, in the semiconductor in the lateral direction will be dominated by the drift current or holes. Of course, you can argue that the minority electrons will also be drifting, but if you compare the two, right, the electron drift current, it's going to be negligible because the concentration is not high. So we just keep it as JP drift.
So it just depends on what type semiconductor you're using, right?
Yeah. What type? Usually the type that you use, the majority carrier will dominate the current.
Okay, thanks.
Yeah. Because of course, strictly speaking, you can take into account all the carriers, but that will complicate the whole analysis. Then you have to deal with also the electron current as well, right? Which, in a general sense, as approximate consideration, it'll be relatively small, so we can actually ignore the effect. It's a secondary effect. Okay.
Prof.
Yep.
Can you explain how you get JP drift from the experiment itself?
Oh, from the experiment? Okay. So what is JP drift? So if you think about it, right, the drift current density, right, as the name implies, is the current density. So I need to know what is the hole current, the drift hole current, divided by the area, right? Okay. So if you go back to the figure, so the hole current is essentially this component here, which you can measure, right? If you put an ammeter in the circuit, you can measure the current that's flowing. Then the other thing that you need is the cross-sectional area, which is this area here. So if you have a rectangular piece of semiconductor, you can just use instrument to measure the D and the W, right? So if you know the D and W, then it's just current divided by D and W.
Oh, okay. Thank you.
Yeah. So in fact, in the Lab 2 experiment, the dimension of the semiconductor will be given to you as well. So, so you use this parameter to do the calculation.
Hi, Prof. Just to follow up on his question,
Yep.
when you say you take the current divided by the area, doesn't that give you like total J instead of JP drift?
Yes, it does. So what's your
As in, wouldn't the issue be that there will be some discrepancy between like J total versus JP drift because you don't take into account like the electrons?
Yeah. So here, generally speaking, if your p-type doping is sufficiently high, you'll find that the minority carrier drift current will be negligible. So it's okay to ignore.
Okay.
Right. Yeah. That's a good question. But because the magnitude of the minority carrier current will be sufficiently small, so most time you can just ignore it. And it will not change the result too much. Yeah. But you're right, it will introduce a very, very small error, which is not significant, so it's okay.
Hi, Professor.
Yeah.
In these experiments, are there any diffusion current inside?
No, there won't be.
Then when will this happen?
Well, okay, under such condition, generally speaking, there won't be any diffusion current. Sorry, what was the question again?
Under what condition will diffusion current take place?
Well, so if you look at the basic mechanism of diffusion, it requires concentration gradient in the semiconductor. So there must be some imbalance in the carrier concentration in the semiconductor. So if that's there, then you will have effect of diffusion. So in general, when you bias a semiconductor through an external voltage, right, in a single piece of semiconductor, you will not get diffusion. Like in this case, it's everything p-type. You won't have a diffusion current effect. But having said that, right, if you put current through a PN junction instead, then you will find that there is indeed some diffusion current that would exist in some part of the semiconductor, which later on Prof. Ang will talk about all this.
Okay.
Yeah.
Thank you.
Yeah.
Hi, Professor.
Yeah.
I'm a little bit confused on why the negative and positive change the direction when from p-type to n-type, because from my understanding, if the magnetic field and the voltage is the same, how come the negative goes a different direction?
Because of the difference in charge of the carrier, right? If you apply the Lorentz force calculation, okay, you see that in this case the holes, right, that's moving from left to right, the velocity is there, and magnetic field is into the screen. So if we do a cross product of V cross B, the resulting cross product will give you a vector that's pointing upwards, right? And you have to also multiply by the charge, which is positive in the case of holes, and your net Lorentz force is upwards. Okay, so the hole get pushed up, right? So the top is positive charge. Now we look at a case of electrons. In this case, remember we keep the same configuration, so conventional current flow from left to right. But if it's an n-type semiconductor, then you're dealing with electron moving to the left. So your drift velocity now is the vector direction is to the left. If you now do a cross product, V cross B, the cross product actually gives you a vector that's pointing down, right? That's your V cross B. However, in the case of electron, remember you need to multiply the charge by the charge of the electron, which is negative Q. So this negative charge actually flip the force upwards. Okay, which means that the resulting force actually pushes the electron upwards as well, like your holes. So the electron will basically accumulate at the top, so you get negative charge on the top. You get it?
It's a little bit hard to digest.
Which part? Is it the Lorentz force, the cross product, or do you agree that the direction of force in the case of electron in this case is pushing it up?
Little bit difficult to get that, but I have another question. Maybe that will help me.
Okay.
So, let's say there's not a semiconductor, and then there's a current in a certain direction, magnetic field in a certain direction.
Yeah.
Will the electron always travel like upward or
no,
down?
no. That you have to look at which direction is the current flowing and which direction is the magnetic field. So, okay, another way to look at this, instead of using the Lorentz force, is to use the left-hand rule. You guys know the left-hand rule, the motor rule? Do you know the motor rule? The one that causes the coil to turn? Okay, so that one you know, right? So that one you can also apply here. So your thumb is essentially your motion, right? If you recall the left-hand rule, if I try and draw. Okay, so your thumb and then your finger and then this other finger, right? Okay, so this thumb direction is your motion, and your index finger is field, the magnetic field, and then the third finger is current, right? Correct? Agree? Yes? Okay, so yeah, so if you apply it to our situation here, the magnetic field is into the screen, right? So this index finger, you point to the screen, and then the current, okay, this current component here is the conventional current, which is left to right. Okay, so if you point your index finger in the screen and your third finger from left to right, then the thumb is pointing upwards. Correct? So that's the force that the charge will experience. So whether it's whole electron, in fact, they will experience the same motion. That means the force that push it up. So whether electron or hole, the electron or hole will get pushed up, which will result in different charge at the top. Right. So in the case of electron, you get a negative charge at the top. The holes will be positive charge at the top. So when you measure it, you'll see a polarity difference. And the polarity difference will tell you whether it's an N-type or P-type semiconductor material. Does it make sense now?
Yeah.
Okay. Anyway, go and think about it, because sometimes these sort of things you need to think through a little bit, and then you try and understand what's going on and you try and figure it out. So either way, whether you use the Lorentz force definition or the left-hand rule, right? The left-hand motor rule, your conclusion should be the same, because the underlying mechanism is the same. Okay. Can All right. Okay. If there's no more question, yeah. So you guys try and run through it again, and then if there's anything that is not clear, you can come back to us during the tutorial and clarify your doubts. All right. Okay. So if there's no more question, we can end for today here. Right. Thank you very much.
Thank you.
Right.
Thank you.
Okay.
Thank you, Professor.
Okay. Thank you. Right.
Thank you,
Bye.
Professor.
Okay. Bye.
Thank you, Professor.
Thanks, Prof.
Okay. Bye.
you.